a quantum special worked start with the obligatory contribute to this at the same up and and FSCD into maybe so hope interesting. Unfortunately, I mean, I guess a little bit, maybe so calculus because and give us some intuition. X is was originally due. So out to show spiders and the X spiders in calculus. Hilbert spaces actually correspond to identifying bases which is so different kinds of spiders. This has an which maybe some of you have seen the that when functional. Okay, so fascinating. Back in I was visiting Filippo Bocchi, who's my close colleague. Um, we ended up doing is when so unitality, right? So this is just the multiplication or the equivalently the distribution multiplication. It's a think about it's a very on one hand, we have diagrams. So for you. Path count. And I let 0 the right. Well, you know, so this is right, and it's a very have application with the system proceeds now. Two. We just in different colors. Consider one, two, two, and the idea why me it's one. I told you slide. Syntax. So this see the standard. This is just by plus the algebra rules. Because any kind of limit ways in which each other. Okay, so type this original system that we drew. The key thing is that if this is the bottom category, what we called SV. What's a linear? What's a relation? First big side, like the system is linear. Sure. Yes. Yeah. Or traditional situations where in this the then I get a for already quite a do a lot of this trend. So I stop as well. I always thought this is so cool, right? But I'm just paper. So going to well. So, so it's different. So it, and I can and I this syntax of Cartesian category functions natural that be the right thing. The thing that we prove, we have to start. I give you my relational theory, string diagrammatic theory. I look at all its models in REL, and if something's true in all something's true in all the models, if and only if I can prove it using this algebraic structure. So it's like a Gödel style completeness. And it turns out that this kind of idea then had legs, and there is this kind of a meta way of doing functorial semantics, right? So the important thing is you need to know this kind of algebraic structure. So I did some work on partial theories where you replace Cartesian categories with discrete Cartesian restriction categories. And the last thing I want to tell you about is how to do first order logic, and that is Cartesian categories with something called first order bicategories. So I've got 5 minutes. 10. Okay, good, excellent. Okay, I started. I was speeding up. Okay, good. So in that case, let's take it easy, because I really want to. This is something which I'm very excited about at the moment, because it's how to do first order logic with string diagrams. So the thing that this Gödel star theorem that I showed you, it's a nice way of saying that when you look at the structure of Cartesian bicategories, this really captures the existential conjunctive nature of first order logic, right? Because REL itself, the way we've defined REL, it captures the what's commonly known as regular logic, or in database theory conjunctive queries, because it's the fragment. You remember, like when you define composition in the category relations, you're using the existential quantification and conjunction, and it turns out that this really picks out logically the existential conjunctive fragment of first order logic. So REL is kind of a weird beast, right? Because there's somehow two RELs which are isomorphic but feel very different. So the usual category relations I'm going to from now on call REL white, but I'm going to talk about its strange cousin REL black. Okay, so it has the same objects, so they're still sets, and ours are still relations. But now, composition, instead of being there exists and, will be for all or. Okay, so I now compose relations. So X is related with Z in R composed S, if for all Y, X are Y or Y as Z. Now, to be honest, I've been doing this now for over a year, and I still don't really have a very good intuition for this, right? Right, I know, I have a kind of a gut feeling for what usual relational composition is. I don't yet have it for this. And identities are just so before identity was, X is equal to, X is related to Y if and only if X is equal to Y. Now it's the opposite. Okay? Now when you think about it, so this as a category, these two guys are isomorphic, right? The isomorphism is just complement. So these are just De Morgan jewels. This is like the De Morgan jewel of REL. And in a sense, just like the usual category relations talks about the existential conjunctive fragment, this guy talks about the universal disjunctive fragment. And since we know since we know a very nice algebraic structure to capture the first part of the story, we also have a very nice algebraic structure for the second part of the story. It's just a co-Cartesian bicategory. And it's really the same structure, but the inequalities go the other way. Okay, so we have these two fragments of first order logic. The question is, what next? Okay, and we have a kind of a slight, we had to be a bit creative with our string diagrams, right? Because we're going to have string diagrams with two different kinds of backgrounds to emphasize which REL are we in at any particular moment, right? So this is the syntax of Cartesian bicategories of relations, which is going to be our syntax, for the usual REL. So whenever you have a white background, this is the usual category of relations, identity is the identity relation, composition is the usual way of composing relations. But I can also do things with a black background. Okay, so in a black background, I'm working in the De Morgan jewel of REL, so REL's weird cousin. So the identity relation is now the inequality relation, and I compose things, with this for all OR. And I know individually what the algebraic structures are. This is, Cartesian bicategories, co-Cartesian bicategories. So what's missing? What's missing to get the full picture of first order logic? So it turns out not very much. And here, you just have to add more Frobenius. So essentially, there is this, first of all, you have to make sense of this thing, right? So we're now throwing in everything together. What does it mean? Well, we have a category or bicategory in which there are objects, there are arrows, but there are two different kinds of compositions and two different kinds of tensors. Right? There's the white composition, white tensor, and the black composition, the black tensor. Now, category theorists have worked out situations like this, and they're called linear bicategories, right? So essentially, I'm just going to say, okay, from now on, I work in linear bicategories. So that's almost the whole story, apart from these four equations, right? So you need to specify that the Cartesian bicategory structure, so the multiplication and co-multiplication, are related together in this particular way, which are called linear adjoints, and also there is this kind of a Frobenius law. Okay, and it turns out that this is the complete story, and the story is going to be presented at LIX this year, and it's joint work with Filippo, Alessandro Di Giorgio, Nathan Hayden. So here's a little worked example. So this is a completely algebraic account of first order logic, right? So here's a diagram that corresponds to the formula there exists x for all y rxy. Here's the diagram that corresponds to the formula for all y there exists x rxy. Now in first order logic, this is kind of like a non-trivial example where you can prove using, let's say, Gensen calculus or natural deduction that this implies this. So algebraically, what that means is using our algebraic theory, we should be able to prove that this is under this in the ordering. Okay, and it turns out, so this is the proof that we have in the paper, this kind of worked example. This is just string diagrammatic surgery in this setting, using completely algebraic reasoning. Yeah, so this is because so we do have a kind of a deduction theorem, right? So the implication can be folded back into the syntax, right? But this less than equal to, you should read it, you should think about it as there exists a proof in natural deduction or in sequent calculus where I start with this as an assumption and I end up with this as the conclusion. That's really what this correspondence is. Yeah, it's very good. I'm coming to a conclusion. Okay, so I just want to just want to end on the on what's kind of different from traditional first order logic when you do it this way. The interesting thing is negation is not a primitive. Negation is not a part of this language. Negation, you can derive it as an operation that takes syntax and gives you syntax, right? And it's just essentially color swap. Black goes to white, white goes to black. So, for instance, neg phi is syntactically equal as a diagram to neg phi, right? Because this is just an operation on syntax. And there's all kinds of, we have a, completeness, we proved a completeness theorem in the style of Henkin. There's all kinds of really cool stuff that I don't have time to get into. And it's very closely related to this field of logic called deep inference, right? Because what we are doing is a completely algebraic way of dealing with first order logic, equals replaces equals. We don't need to develop particular proof theories, it's just algebra. Okay, this is my last slide. I want to end on some philosophical ramblings, which I think as you get older, you get more and more allowed to do this, right? I tried to do this when I was young and people really hated it, so I'm still a bit nervous. So I think in general, a big chunk of algebra can be understood as patterns where Frobenius and Hopf algebras or bialgebras interact in some way, and ZX is one important example. And I think that these two algebraic structures seem to be really fundamental building blocks of reality, and somehow at a higher level than we normally do maths. What I didn't talk about is probability theory. I think that's there's a whole section of people who are now working on string diagrams for probability theory, where the underlying categories are Markov categories. And I think it's a really important topic that's going to see a lot of great stuff coming in the next few years. And finally, I want to kind of make this thing of string diagrams are the syntax for the 21st century. So why? They are resource sensitive out of the box, which is crucial for things like quantum, right? And moreover, they expose, and I've seen this time and time again in many different fields, once you do it properly with string diagrams, you see a lot of hackery and sometimes lack of rigor, implicit assumptions, and outright mistakes caused by the use of traditional syntax. But there is this one thing which I think is holding us back, so we need more tool support, diagrammatic editors, diagrammatic theorem provers, etc. That's it. That was my final slide. Thank you very much.
Sugar in your ZX approach, which I found really, really sweet. And then two trivial questions. First of all, can one then combine two white and black cousins and they would essentially equal out, or is that too trivial to think about? And the second question is, what are the implications of the recent Continuum paper, basically saying that ZX calculus is complete in what's the finite dimensional Hilbert spaces?
Yep. Okay, so I'll take the last question first. So the completeness, so that when people talk about completeness of ZX calculus, it's a slightly different kind of completeness, right? So when I talk about completeness in here, I mean completeness in the style of Gödel. So I have some kind of a syntax, and I have a way of giving models to the syntax, so giving semantics. And Gödel's style completeness says that if something is true in all models, then I can prove it already at the level of my syntax using my algebraic theory or using my proof theory or whatever. So this is Gödel completeness. Now ZX completeness in this is something different. It's about capturing all of the structure, all of the relevant structure of Hilbert spaces using your calculus, right? So it's essentially can we express every matrix, every unitary using this approach, right? And so that becomes a very technical issue because you have to, because for example you have to, because in the end you have a finite language to express uncountably many things, right? So there's uncountably many complex numbers, right? So you have to state this carefully, and the proofs are very complex, right? So it's obviously very important because you want to know whether your language is. Because in ZX, you're only really interested in one model, right? There's not really other models that you're interested in. You're interested in the model that's relevant for quantum. So it's about being complete with respect to that. So it's more like, I guess it's something like more like Gödel's. It's a kind of a completeness that's more like in Gödel's incompleteness theorem, right? Because Gödel's incompleteness theorem is about really a particular model, which is the naturals, right? The integers. And the other question about collapsing real white and real black. Yeah, this is kind of a really weird, like for a long time, this was a mental block for me, right? Because real white and real black are isomorphic, right? So once you know that two things are isomorphic, what more can you say? Like as a mathematician, that seems like the most strong thing you could say, and the question is over, right? But somehow they're isomorphic, but in order to get first order logic, you have to separate them and understand how they interact, right? So that's really where the meat comes.
Any other question?
Yeah. Last line. Is this amenable to Koch proofs?
Is it amenable to Koch proofs? Yeah. I mean, so I don't. I think one can approach the question of what it means to be a diagrammatic theorem prover in different ways, right? So clearly one way where one could start is just using the string diagrams as syntax, then translate down to terms and use Koch as the back end. So that's certainly one future direction where I think we can make progress. Another way is just to have a completely diagrammatic back end where you actually do graph rewriting and matching given a particular theory, and maybe things like e-graphs then become interesting in this setting and so forth. I really feel like that this is where a lot of attention needs to be put for this stuff to become more interesting than just mere. I mean, there's also the problem, right? These things get kind of difficult to draw on paper with a pen, right? So even though they give you a lot of, I think they give you a lot of intuition after a while when you play with them, they're still kind of a pain to draw. So having tool support for applications like this would be amazing.
So following up on this, we already had two-dimensional software, notation in the beginning of the 20th century, and it was basically abandoned.
And you're talking about existential graphs?
No, Russell and Whitehead.
Oh, right, yeah, so sure. And also the original, by the way, the original paper by Frege on quantifiers.
Yes.
Was
so
right?
There are a number of attempts actually of capturing semantic properties in syntax. So basically you're capturing certain equational properties in the syntax itself and so on. But when it comes to actually representing these things as data structures on computers, I mean, what you're suggesting is like, taking planar computers or special data structures. And here's the second question. It turns out actually, very often actually building in equations or equalities into the data structure is actually not a good decision. So for example, our coordinate-based approaches in physics, for example, the theories are coherent, but we're working with matrices, even though, you got coherence problems, and you're exploiting actually that you don't have to have a unique representation of the semantic object.
Yeah.
So, okay, can you speculate some more, please?
Sure. Sure. So first of all, I agree that one of the areas where we've made a lot of advances in the last 10 years is precisely to stop thinking to have because I've talked about these things as syntax. And I've talked about these things as algebraic structures. I haven't really talked about them as combinatorial structures, so something like an underlying data structure. So there is a story. There's a story that I didn't tell today. So we do have a very good understanding of string diagrams, at least a very wide class, with what the data structure should be and how the algorithms should work. So there's a whole series of papers which I'm involved in called string diagram rewrite theory, where we really do rewrite. We really developed the theory of rewriting on this. And there has been some toy tools worked out using this methodology, but nothing sort of at the size of, let's say, a Koch or a Lean. Or now the other question was, is it actually a good idea to bake in a lot of these equality into the data structure? So I think it's certainly. I mean, so when you look at e-graphs, the success of e-graphs, I mean, that's precisely the idea in e-graphs, right? You bake in equality into the data structure. So I personally think that has legs, but yeah, again, this needs to, I think it's definitely worth trying and seeing what happens. But thanks for the question.
Any other question? Just a quick one, very short. These algebraic structures and their interactions are used to. Can you hear me? I don't know.
Yeah.
For describing circuits, right? For the purpose of optimization. So do they really? Are they able to capture entanglement? I don't see it.
Yes. So there is.
I mean, I couldn't say it, but maybe I missed it.
So I didn't talk about that. So unfortunately, this wasn't a ZX calculus talk. But yes. So they capture entanglement. They do things like quantum teleportation.
Okay.
And I'm told. I mean, again, I'm not a big expert, but I'm told that more and more ZX calculus is actually being used in industry or being used in industrial relevant applications for things like quantum error correction and things like this, right? So these are. It seems like people are finding this calculus very useful in the sort of quantum domain.
Okay. Yeah. Thank you.
Thank you. Thanks. It was a pleasure.
And let's move to the